All right, so chapter 5 will be about probability. Okay, so at the beginning of our course, which feels like it was a long time ago, but it was just 2 weeks, like 10 days ago, right? During summer we just move on incredibly fast. It's the equivalent of fourth week already in regular session. So 10 days ago I said in statistics we start off with descriptive statistics. We learn how to describe our data, and I argue that we wrapped that up with Monday's lecture. So we learned how to describe numeric data with the mean and the standard deviation. We learned how to describe categorical data with frequency tables and percentages, and we learned how to describe relationship between two numeric variables via correlation. Okay, and then in order to make inference or make conclusions based on our data, we have to have an understanding of probability and probability distributions. And so here we are going to start our section on probability. Okay, and because ultimately when we perform statistical inference, okay, so just to kind of put things in in the big picture, when we perform statistical inference, okay, there's a question that we have in the back of our mind. Okay, we wonder, could the data that I observe be a result of random chance? Or does the data indicate that something else is going on, something, quote, interesting is going on? Okay, and I know this is kind of this vaguely formed question, but a lot of times we're asking, could the results I see be a result of random chance? Okay, could the data we observe be a result of random chance? And so in order to answer that, we need to understand probability. Okay, so we must and we are going to say that probability describes how likely or unlikely or unlikely a particular outcome to an event, unlikely an outcome is. Okay. And so we have this this concept of randomness. Okay. We also have and so randomness means that the outcomes are unpredictable, okay? Okay. Okay, and we do not expect to see, or there will be no pattern. There's no predictable pattern either. Okay. Random is different from arbitrary, okay? So when you roll, rolling a die or a single dice, okay? So here's your six-sided die. Okay, so rolling a die, the outcome is random. Okay, we cannot predict with any kind of certainty what the next roll will be. Okay, and there will be no pattern. After many rolls, okay? So we say that the outcome to a die roll is random, okay? At least in the context of our class. I guess there's a question of what is random, and we could debate, is the outcome to a die roll truly random? And someone could argue that it's just a result of the laws of physics, so that if we knew the exact velocity and the exact angular momentum applied to the die when we release it from our hand, we might be able to predict exactly how it should roll and how it should land. Okay, and the same could be said about coin flips and all of these other things that that we might consider to be random. And so there's kind of this question of, what is random and what isn't. But I think, for most people, we will accept the idea that that rolling a die, as far as we humans can tell, is random, okay? And so, that's how, so casinos have accepted this, and that's why they'll let you roll dice and place bets, and they'll take your money if happily, okay? So we have that, okay? And so when we talk about probabilities, we can say things like the probability of rolling a 6. I can make a statement like the probability, we'll say, of rolling the number 3 is 1 out of 6, okay? And we'll have to talk about exactly what we mean by saying the probability of rolling the number 3 is 1 in 6, okay? And so this statement, and let me copy this onto the next page. This statement is what we would call an example of a theoretic probability, because the way I got this 1 in 6 is I said, well, something along the lines of there are 6 sides to the die, okay, and each side is equally likely. So the probability of getting the 3, which is on one side, is 1 in 6. Okay, and this is an example of a theoretic probability. Okay, and so a theoretic probability is a probability based on the kind of the mathematical rules or axioms in probability. So it's just based on kind of our mathematical rules, which we might call axioms, and we say this is the theoretic probability. And that's so 6 sides, each side being equally likely. Getting a 3 will be 1 out of 6. Okay? Okay. Let's say somebody hands you a funny shaped die, okay? So this die looks, I don't know. I'm trying to draw something and, okay, so here's it's 3 and 2 and then there's other sides, okay? This is a funny shaped die. Okay, so now you no longer feel like the sides are equally likely. Let me just draw kind of a line here. Okay. However, you can still roll it, and the outcome is still random, okay? The outcome, we can still roll it, and the outcome is still random. Meaning that we can't predict the outcome, and we can't, we're not going to see any kind of pattern. But we just don't know. No longer can we say that the probability of getting the 3 is 1 out of 6. Okay, so if somebody says, what's the probability that we get the number 3 now? Can you answer this question? Is there anything we can do to get an idea of what this probability is? Do we just say this is a mystery of the universe that we'll never know the answer to? You guys all nod your head like, oh, okay, that's fine. So we might not be able to use, because it's a weird shape, okay? And perhaps we haven't studied, I don't know what branch of mathematics would be applicable here, but like some kind of stochastic topology or something like that. Because we haven't studied this, we might not be able to use math, okay? And we might not even understand how the math and the physics need to be applied here, okay? But there's a rudimentary yet very effective way of estimating the probability, okay? We can still estimate this probability using what we call an empirical probability, okay? So if we wish to know the probability of rolling a 3, okay, we can no longer use math, no longer just say it's 1 in 6. but we can estimate it empirically. Okay, and so what do we mean by that? Well, we can just hire someone and say, please roll this die. Okay, maybe we don't even have to hire someone. Maybe we can make a robot to do this. And we can just say, please roll this die 10,000 times and record how often it lands on the number 6. Okay? So we do an experiment. We conduct an experiment. Okay, and we say, we roll the die 10,000 times. Okay, and let's say it lands on 3 2,745 times. Okay, so we can estimate the probability. We have an empirical probability, which is going to say that the probability of rolling a 3 is about 2,745 divided by 10,000, or 0.2745. And so the next time we roll the die, we can't predict exactly how it's going to land, but we can say that the probability that it will land on the 3 is somewhere around 27.5%. Because when we rolled it 10,000 other times, it landed on the number 3 with about that probability. So we expect that probability to carry forward. Does that make sense? So this is what we call an empirical probability. So an empirical probability, I'd like to flip to the next slide. An empirical probability is a probability based on multiple trials. Okay? So here we've actually conducted an experiment. Because we couldn't figure out, we don't know the math going into it, we just ran an experiment. We rolled the die a whole bunch of times, we got a number, and that's our empirical probability here. Okay? Is that okay? All right, so an empirical probability, just to kind of further define it, is a probability based on actual trials, okay, or simulations. Okay, we repeat the trial or experiment many times. And find the relative frequency of a particular outcome. Okay. So this is empirical probabilities are useful anytime the math gets too complicated for us to figure out the theoretical probability, okay? So we use empirical probabilities when the math to find a theoretic probability gets too complicated. So an example where we use empirical probabilities is kind of sports forecasting. Okay, so sometimes before a big game, they'll say this team has a 62% chance of winning. Okay, or this team has a 25% chance of winning the championship title. Okay, how are these things calculated? Well, there's no formula that just says, oh, plug in, I don't know, the stats of your players and the past team performance and figure this out. Okay, a lot of times computers will run simulations, and they'll simulate games between these two teams playing, and maybe in one simulation this team wins, and in another simulation the other team wins. But after maybe 10,000 simulations, you'll see that one team has won 62% of the time, and that's how they're getting that number. Okay, so if you have a video game system, you might have like Madden or something, and you can set it up so that your video game system the computer can play against itself, right? You can have the computer play itself and see what happens. And that's basically one simulation for a game, okay? But, just do this at a, industrial level where you're running like 10,000 simulations and you're having the computer play against itself based on, its simulated model, and then have it try to estimate the probability of winning, okay? And so that would be an example of an empirical probability. Okay, the rest of our class, or in our class, we're going to focus primarily on learning the rules for calculating theoretic probabilities. Okay, so we'll talk, let me just write, example of an empirical probability will be like, computer simulations to estimate probabilities for sporting events. Okay, but again, the rest of our class is going to focus on learning the rules for theoretic probabilities. Okay. So we'll start to define this. Okay, and so we can start off by saying that we have some event A. Some event A, and this is, the outcome to a random experiment. Okay, and so A is the particular outcome that we are interested in. Okay, then we have the probability of A. Okay, the probability of A happening is P of A, okay? So also written probability of A, okay? and this is a number, the probability of A is a number that expresses, it's a number expresses how likely A will happen. Okay? And we say the probability of A is always between 0 and 1. So whatever event we're talking about, the probability of A is between 0 and 1. Okay? And if the probability of A equals 0, then A never happens. It is impossible. Okay? And if the probability of A is equal to 1, then A always happens. Okay? Or A is certain. And anything in between basically indicates that the probability is some other number, okay? And I saw a meme on the internet, and it was, well, everybody sees memes on the internet, but, and it was basically, it was like Velociraptor, and it said, if the weatherman says, or weather person says there's a 50% chance of rain. Does it mean he doesn't know if it will rain? Or something like that, okay? And what's the answer to this question? Yes, no? All right, who thinks yes? There's like 8 of you raising. Okay, and who says no? Okay, well, all right, so thank you for participating, those of you who raised your hand, and everyone else, boo on you. Okay, so if the weatherman says there's a 50% chance of rain, does it mean he doesn't know it will rain? That is correct. The weatherman does not know if it will rain, okay? All right, but let me just change this, okay? If the weatherman says there is a 95% chance of rain, does that mean he doesn't know if it will rain? And what's the answer here? Okay, and the answer is still, yeah, he doesn't know if it will rain, okay? Because really, we can't predict the future, okay? And only if in cases of 0% or 100% chance of something happening can we say we know that something will happen, okay? Otherwise, there's still a 5% chance that it won't rain, okay? And we don't know if it's going to rain or not, okay? Now, 95% chance of rain It means it's probably a good idea to pack an umbrella and probably be a good idea to prepare for the rain. But is it possible that you pack an umbrella and you step outside and it's not raining? Yeah, that's still possible, okay? So just keep that in mind, okay? All right, we have what we call the complement of an event. Okay, the complement spelled with an E, so not, it's not a nice thing we say, but the complement is the kind of the event where it does not happen. Okay, so the complement of event A is the outcome where A did not happen. Okay, so we might say we can write this as A complement is the same thing as not A. Okay. So if A is the coin lands heads is equal to the outcome the coin lands heads, what is the complement of A? Not A would be the coin does not land heads. Okay, and we can say we're going to simplify the world so that the coin not landing heads means the coin lands tails. Okay, so we can simplify and say not heads means tails. But technically, the coin not landing heads includes all the scenarios where the coin didn't land heads. So maybe lightning strikes the coin midair and it disintegrates or something, you know, or I don't know what else could happen to this magical coin. Or, you know, maybe it lands on its side, or maybe it rolls away and down the gutter. I don't know, goes on an adventure without you. So the coin, so the complement of A would be just A does not happen. Okay, now a lot of times we simplify things and we just say, well, not heads means tails or something like that. But I think there was a recent soccer game where they flipped the coin and it landed on its side or something. And so stuff like this still happens, okay? And the rule is that the probability of not A is going to equal 1 minus the probability of A. Okay. So if A has a 80% chance of happening, not A has a 20% chance of happening. Okay. And I just so you know, I kind of use percentages and proportions almost interchangeably. So I might say 0.8, probability of 0.8, or I might say probability of 80%, and I hope that's fine with all of you, okay? We have simple outcomes, okay? So in some scenarios, all outcomes, or I should say, yeah, all outcomes have the same probability. So this could be things like flipping a coin, where your outcomes include heads or tails, both equally likely. Or, you know, rolling a die. We have the outcomes 1, 2, 3, 4, 5, and 6, all equally likely, okay? Or, you know, selecting a random card. Okay, so each card, okay, and all cards have equal probability, right? Okay, and then so we might have some event A. So A is an outcome that consists, or A is an event that consists of several of these outcomes. Okay, so maybe I'll, let's say I pull up a deck of cards. Okay. View image, copy, paste. Okay, so here is a deck of cards. There's 52 of them, okay? 52 cards, and I say, let's say A is the event, is you draw a face card. Okay? So what is the probability? The probability of A, if all of these outcomes are equally likely, the probability of A is the number of outcomes in A, and we're going to divide that by the total number of outcomes. Okay. So, how many outcomes are included in drawing a face card? Okay, so a face card would be the cards with faces on them. So that's a jack, a queen, and a king. Okay, so as far as face cards go, this is a face card, the jack of clubs, queen of clubs, king of clubs, okay, the diamonds, the 3 cards in the diamonds, the 3 cards in the hearts, and the 3 cards that are spades. So we have 12 cards. 12 cards are face cards. We have a total of 52 cards. So the probability of A is 12 out of 52, which reduces to 3 out of 13. Okay, and we could put that in decimal form, but fractions are also fine. Okay. This thing, number of outcomes in A divided by the total number of outcomes, this only works if the outcomes are all equally likely. Okay? So for example, if I said I will flip a coin twice, okay? And I can ask, what is the probability that the coin lands heads one time? Okay? So the wrong way to do this would be to say the outcomes, possible outcomes, are coin lands heads 0 times, heads 1 time, and heads 2 times. So this would be 3 possible outcomes. So getting 1 head equals 1 out of 3. This is wrong, okay? Because these outcomes are not equally likely, okay? Okay. It's the wrong color. What happened? Okay. So the correct way would say the possible outcomes are heads, 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 tails, tails, heads, and tails, tails. Okay, so we have 4 scenarios. Four outcomes. Each are equally likely. Okay, and then so the probability of getting 1 head is equal. We have 2 outcomes, heads, tails, and tails, heads, divided by 4 outcomes would be 2 out of 4, or 1/2. Okay, so far so good? Great. Okay, we can talk about combining events, okay, with and or, okay. Okay, and so we have, you know, A and B and things like that. So we can say A and B. Let me get my okay. Well, anyway, so you know, A is this, okay, and then B is this, and so A and B would be just the part that overlaps, okay. just the overlap, or the red area, okay? And then we have A or B, okay? And in statistics, this OR is an inclusive OR. And I'll explain what we mean by that. This is going to be the green plus the red plus the blue, okay? So it's everything together. Okay, so it's any area covered by A or by B or by both. Okay, so it's when we say or, we mean and or. Okay. So, you know, I could ask you, do you like? Because in English we have this little bit of ambiguity in our language. We say, you can ask someone, hey, so do you like chocolate or vanilla ice cream? And then and the person would respond, what? I like chocolate, or I like vanilla, or something like that. Okay. I could ask the exact same question and say, hey, do you like chocolate or vanilla ice cream? And then the person would send, now the answer would be yes or no, okay? And so in one of those instances, just based on kind of the intonation, you have an exclusive or, where you're expecting the answer to just be one thing or the other thing, okay? And in the other case, you have an inclusive or, where it's you either, you know, you like one or the other or both, or you don't, okay? And so in statistics or probability, whenever we see the word or, it's the inclusive or. It's do you like A or B or both? Do you like chocolate or vanilla ice cream? Yeah. Sure. So that's what we have here, okay? And so we can we can create a table, like you know, do you have a cat versus no cat? And do you have a dog versus no dog? Okay, and we can say something like 30% of people, I'm making these numbers up, okay, have a dog. And we'll say 25% of people have a cat. And we will say 10% of people have both cat and dog. Okay. All right, so let's, I'm going to put 100% here. So if I say 30% of people have a dog, I'm going to put what? I'm going to put a 30% here, and what goes right here then? How many people don't have a dog? 70%, okay. 25% people have a cat. What percentage of people don't have a cat? 75%, okay. All right, and then and it says 10% of people have both a cat and dog. Where does that number go? Yeah, this corner right here, right? Okay, so if 10% of people have a cat and a dog, how many people have a dog and no cat? 20%. Okay, if 10% of people have a cat, how many have a cat but no dog? 15%, and then what goes right here? 55%, right? Okay, we could also kind of say, I could say over here I've got dog, and over here I've got cat, And let's see, what is the best color to use here? So in the middle, I'm going to put in what? What goes in the middle here? What's in the overlap? 10? Okay. And what goes over here? So this is, what value goes in the blue? This is people who have a cat, but no dog, right? People who have a cat but no dog. And in total, 25% of people have a cat, right? So I've got to put in 0.15. Are we satisfied with that? Okay. And what's going to go over here? 0.2, right? And then in the corner, for everyone who doesn't have a cat or a dog, that's 0.55. Okay, so whether you draw it this way or you draw it with the table, you pretty much have the same info, right? Okay, so I could ask the question, what is the probability of having a cat or dog? And you would answer the answer here is 0.45, right? How did I get that? We're going to do people with a cat and dog, people with a dog and no cat, and people with a cat and no dog. Okay. There's another way we could do this, okay? I can say we're going to take everyone who has a dog, okay? This can also be probability of dog plus probability of cat, okay? So I'm going to just take the whole circle for dog, which is 30%, and I'm going to add the whole circle for cat, which is 25%, okay? But what happens if I do that? I've added this middle part twice, right? So I only want to include it once, so I'm going to subtract off the overlap here, okay? So I'm going to do probability of cat and dog, and so I would have 0.3 plus 0.25 minus 0.1, and I also get 0.45. Do we see that? Okay. Or another way you can think of it is we're going to take this whole circle for dog, which is 30%, and I don't want to actually add this whole circle. I just want to add on just the blue part, okay, kind of the crescent or this part over here. So how would I calculate that? Well, it's the circle, the cat, minus the overlap, minus the cat-dog part. So basically I'm doing circle for the dog plus, and you can kind of think of if we put a parentheses around cat minus cat and dog, it's just adding the blue part right there. Is that okay? All right, why don't we, we'll take a 5-minute stretch break here, and then we'll continue on with all of this.